Okay, there we are. Good morning, lads and ladies. Welcome back to MAC1140 pre-calculus. Today we're going to continue talking about functions. We're going to learn a fair deal more about functions, specifically their graphs. We're going to take things kind of gently, but hopefully some of this is new to you. And even if you've seen it before, hopefully you get a little bit more understanding than you might have in a previous algebra class. I'm going to turn on the document camera and the screen share here. All right. And then just to kind of keep you guys up to date with the homework situation, let me show you what's going on over there. So you guys are section 008. You do have a new homework that came out today. I had intended, if you look at the syllabus, I intended this to be both sections 3 and 2.4. But my class yesterday, my MAC1140 classes yesterday, we weren't able to get through to 2.4. So I'm thinking since this class has the same runtime, probably we won't get there also. So this homework for the weekend is somewhat light. It's just section 2.3, and then we'll hit 2.4 at the start of next week. If we have extra time today, we may talk a little bit about 2.4, but we'll see. I'm not expecting to. So as always, this is MAC1140. Section number is 008. That's pre-calc. And today is the 2nd of September, 2021. Today we're going to talk more about functions. Graphs. Specifically, we're going to look at section 2.3, which is on getting information from the graph of a function. So for example, I've shown you some ways to find domains, right? Just using algebra. There's some algebra things we can do to find domains. Look for those red flags, solve the corresponding equation or inequality. If you happen to have a very good graph of your function, you can also find the domain that way. In addition to that, you can find the range, which is something that we really aren't able to do super cleanly using just algebra. It's not always an obvious way to find a range, at least not anything super simple. And then there's a whole host of other things we can do. We can find where a function is increasing, decreasing, we can find minima and maxima, and we're going to talk about something called net change and average rate of change if there's time. I think net change, remind me really quickly, did we cover net change on, we did, okay, good. All right, then we are where we thought. Let me see, is there anything else that I should mention at the start of class? I saw a quick question there. So the homework that opens today is due next Tuesday at the start of class. That's correct, yes. Oh yeah, of course, the other thing we're gonna do here, solving inequalities in equations graphically. Did we do that last time? I don't think we did, no, okay, good. All right, I was trying to remember, where did that other class time go? I thought it's just those things, and we should have more than enough time to get to 2.4. But the graphical solution of the equations and inequalities, that's a pretty big deal. So we want to take the time to give that the respect it deserves. Coffee and we can get started. So I'll say recall that the domain of a function is the set of all inputs or x values, if you're thinking about it on the graph, and the range is the set of all outputs or y values. So one of the first things we want to do is figure out how to find the domain and range of a function, just looking at its graph. And to do that, we play what I call the smooshing game. It's silly, I know it sounds like a childish thing, but I promise you it works. It works. This is a sound way to think of things. So let's do it. This section can be a little bit frustrating because at this point, you guys don't know much about how to graph lots of different functions. Graphing is on its own kind of a labor-intensive thing. So generally here, I'm going to provide the graph for you, and then we'll just work from that graph. And then later in the term, we're going to talk about all the little tricks for graphing complicated functions. But the trick I'm going to show you for finding domains and ranges is I'll call it the smooshing game. And smoosh is probably not a real word in the English language. There is a mathematical term for this. It's called projection. What we're really doing is projecting the graph. But let me show you what I mean. Start over here, something like this. Maybe that comes up here like this. At this x value, just continue that. And then maybe this is open over here. All right. So let me pretend like this is -1. This is +1. This 1, 2, 3, 4. And over here, this is 1, 2, 3, and 4. 5. So what I'd like to do is find the domain and range of this function f of x. We did see last time where functions like this can come from, right? It's not hard to imagine this as a piecewise function. It's some sort of quadratic, something giving me like a parabola from -1 to 1. And then for x's between 1 and 4, it's behaved like some sort of constant function, looks like, right? A nice horizontal line here. I'm getting a little bit sick, so I apologize. My body isn't quite doing exactly what I want it to do. I'm a little shaky, but hopefully we can all kind of see what's going on there. In order to find the domain, what we do, the smooshing game, in order to find the domain, what we're looking for is the set of all x values on the graph. And the easiest way to think of that geometrically is like you've got a big hydraulic press that's going to come in here and go and smush the whole thing down onto the x-axis. All right, you can take that whole graph. Or another way to think of it is you've got a light up here, a very bright light shining down, and then you're looking for the shadow along the x-axis. That's where the term projection comes from in mathematics. So to find the domain, you smoosh the graph onto the x-axis. So you imagine this point right here, if I just smoosh him down, he's going to hit -1 right there. So -1 is definitely included. And you think about all the points on this little arc here. This guy would get smushed down to here. This guy gets smushed down to here. A point right here would get smushed down to right here. All of that stuff until you get to this guy. And this open circle, remember, there isn't actually a point at that open circle, so he wouldn't hit anything here. But above him is this closed-in circle, so he is going to come down and hit this one right here. And in fact, we can continue on, right? Because the next part of this line is going to come down and smoosh onto the x-axis here. This is going to come down and smoosh onto the x-axis here. Everything out to here, right? Again, think of it as a bright light up here, and I'm just shading, drawing a little shadow down there. Or you can think of it like something is pressing all of this down on. When we get over here to the 4, I ask what part of the graph is going to smoosh down to here. Well, like just to the left, this little piece right here is going to get smooshed down to here. But the circle at this end is open. There's not actually a point on the graph there. So nothing hits the 4. The 4 is left alone. So kind of down here in purple, you see what we would get if we smush the whole graph down onto the x-axis. So that shaded purple interval down there, that's your domain. So the domain here is the left closed, right open interval from -1 to 4. Are we all clear about where this is coming from? Any questions about how we got that shaded interval on the graph or how we translated that into the interval notation? Okay. The range is a little bit more complicated for this particular function, but it's not that bad. We're going to do the same sort of thing to find the range. You want to smoosh the graph onto the y-axis. Because remember what the range is, it's just the set of all the y values on the graph. You know, you imagine there's definitely infinitely many points on this graph, right? This graph is kind of a solid connected piece. Even from -1 to 0, there's infinitely many points on the graph right here. But if you had a list of every single point on the graph, then the domain would just be grabbing the x values from every single one of those points. And the range would just be grabbing the y values from every single one of those points. But because there's infinitely many of both, it's certainly easier to write them as intervals. So we want to take all the y values that are on this part of the graph together with all the y values that are on this part of the graph up here. So let's think about it. If I come in and start smooshing things, this part of the graph right here is going to get smooshed onto the y-axis right here. In particular, this point is going to come over to 2. All right, there's a point down here at 0, 0. It's a little bit hard to see, but our range looks like it's going to start down there. This part of the graph, this piece right here, when I smoosh this in, is going to hit everything from 2 to 3. But it's not going to hit 3 because this point is open. There isn't actually a point on the graph there. So I would put a parentheses there. And then this whole portion here, the y values everywhere along this part of the graph, they're all 4, right? Like here's 1, 4, 2, 4, 3, 4, 3.5, 4, 2.5, 4, 1.7, 4. This whole thing here smooshes over to the single y value 4. So the kind of vertically shaded blue interval there is the range. I shouldn't say interval, only part of it is an interval, right? This is an interval. That's the interval from 0 to 3, left closed, right open. But this is just a single number. So the range, we have this piece, which is the interval from 0 to 3, closed on the left, open on the right. And then I have to union that with just the single element 4. And the way we would write that is union. And then remember, if I want to write a set that has just 1 or 2 things, I just put those 1 or 2 things in curly braces. So that would be my range. Okay, there's a couple questions in chat that I want to address. Where did the 4 come from? So this whole portion of the graph, imagine I'm like gonna push this whole thing over and flatten it against the y-axis. This whole part of the graph is going to get flattened onto the number 4 there. So for the domain, we push everything onto the x-axis. For the range, we push everything onto the y-axis. Example, here I have the point 1, 4. Here I have the point 2, 4. Here I have the point 2.3, 4, right? Every point along this portion of the graph has y value 4. So when I smoosh this part of the graph onto the y-axis, that whole thing just piles up on 4. So that's where the 4 is coming from. And because that's not an interval, it's just a single point. The way we would write it is as the set containing the single element 4. The other question is, when do we use the union? Well, if your domain or your range or whatever set you're trying to describe happens to be a few intervals, right? Maybe they're not all connected. Then you would put those together as a union. It happened to be the case that my domain here was a single connected set. When I smush all this stuff down onto the x-axis, not everything between -1 and 4 gets hit. Nobody gets missed. But in the range, right, there's lots of stuff that gets missed. There is no part of this graph that has y value 3.5, for example, or even 3, right? There's no point on this graph whose y value is 3. There is a point on the graph whose y value is 4. There's lots of them. All of these have y value 4. So 4 gets hit. And down here, this portion of the graph includes y values all the way from 0 up to 3, not including 3. So everything between those get hit. And that's exactly when we would use a union. It's when I need to discuss a set that is made up of multiple connected pieces. So I think that's, is that satisfactory, Chris, regarding the union? Cool. Okay, good. And Mel, are we comfy with the 4? Was that what you were asking about, or was it something else? Are you asking about the 4 in the range or in the domain? In the domain. Okay, yeah, let's come back and talk about that then a little bit. So when we're talking about the domain, we want to flatten everything onto the horizontal axis, onto the x-axis. So kind of, let's look just at this piece for now. If I take this and bring it down, I'll do some black maybe. This point and I smoosh it on down, he's going to hit this point right here. If I take this point and smoosh it on down, he's going to hit this point right here. If I take this guy and smoosh it on down, he's going to hit this guy right here. So this line segment is going to hit all this stuff, right? Imagine it just falls and goes splat onto the x-axis. Every point along this line segment is going to hit some point along the x-axis here. So this guy hits 1, this guy hits 2, this guy is going to hit 2.3 right in here. The only weird thing that happens there is this open circle. So remember, when we draw things like this open circle is kind of big, right? It really should be infinitely small. It should be the size of a single point. But I don't have a pen sharp enough to draw an infinitely small circle. So the way we kind of, the notation we use for that is the open circle here. So there is no point on this graph whose x value is 4. It gets, you've got 3.9, you've got 3.7, you've got 3.99, right? Right in here is a point. Right in here is a point that's like 3.9, 4. And that point is going to project or smoosh down here to 3.9 along the x-axis. But there isn't actually a point here on the graph. That's what the open circle signifies. So everything up to 4 has a point on this line, but x equals 4 itself does not have a corresponding point on this line. So we'd say the domain is everything up to, but not including 4 itself. That's open intervals are weird, right? They genuinely are strange things. So when we do that with every piece of the graph altogether, this stuff would hit -1 closed to 1 open, and this stuff would hit 1 closed to 4 open. And when you kind of look at all that together, that turns into this. If you want to think about the domains as separate pieces and union them, you could do that. That's not incorrect. I could describe this set, and maybe this is a little bit more intuitive, as -1 to 1, left closed, right open, union with 1 to 4, also left closed and right open. So this piece has this domain, and this piece has this domain. But when you union those together, you get this. And it's nicer to give that like this than it is like this, but both would be correct. Okay, so domains and ranges, not terribly hard, as long as you have a really good graph, right? As long as you have a graph where you can actually see all the x values and all the y values, you can play this smooshing or projection game in order to find both the domain and the range. And up until now, we didn't have a way to find ranges, so this is good shit. Once you can tell what all the x values and all the y values are on a graph, the natural thing to do is to start trying to answer questions about that function. There's a lot of stuff beyond domain and range. Specifically, if you have two graphs that are very good on the same coordinate axes, same plane, you can start comparing them. So I don't remember if it was in this group or one of my other classes, but somebody, when we talked about inequalities last week, was asking, how do I solve those graphically? That's what we're going to look at now, solving equations and inequalities graphically. I'm going to draw a kind of general picture to start, and then we'll look at a specific example. I'll use some color here. Okay. So I have a function here, f. Here, call it G. And kind of assuming that they don't do anything weird after this, like let me send this guy back up so we don't have to worry about them crossing again. We can compare f and g at a bunch of different x values. And that comparison is going to turn out to be the idea that you need in order to solve an inequality. I'm going to label these two x values where the functions touch as a and b. So the reason I modified the purple one to kind of turn around and go back up like this is because I don't want them to touch again, just for simplicity's sake. I want to assume they only touch twice. The point right here on the graph, all right, let's think about the blue graph first. That would be the point A, comma, G of A. If we think about it being on the purple graph, then that would be the point A, comma, F of A. Now, they both have the same x coordinate. They both have x coordinate A, But the big deal is that because these graphs touch, the y coordinate is also the same. So here, this is, on the one hand, it's f of a. But then when you think about it being on the blue graph, that y value is also g of a. So what's going on here? Well, this x value where these two graphs touch are solutions, or is a solution to the equation f of x equals g of x. So points where the graphs touch tell us solutions to the equation f of x equals g of x. Solutions to an equation like that are going to be just x values, right? Just numbers. You can imagine, if I gave you an actual function f and an actual function g, like x squared and x minus 3, the solutions to that equation, x squared equals x minus 3, that's just going to be a couple x values. But if you're trying to solve an equation graphically, you need to graph both sides of the equation as their own thing, and then look for points where they touch. So here, the solutions to f of x equal g of x, x equals a, the x value over here where they touch, and x equals b, the x value over here where they touch. So that's equations, right? If you want to solve an equation graphically, graph both sides, and then look for points where those graphs touch. Inequalities let's say f of x is less than g of x. Is asking where is the graph of f smaller than the graph of g, or where are the y values on the graph of f smaller than the y values on the graph of g? In other words, where is the graph of f beneath the graph of g? So a quick tip: in mathematics, the word where, especially in calculus and analysis, the kind of broader field that calculus is a part of, where always means for what x values, for what inputs. So for what inputs or x values is the graph of f beneath the graph of g? You kind of look one at a time, right? Here's an x value. I'm not even going to label it. But at that x value, the graph of f is beneath the graph of g. So this x value, whatever it is, would be a part of that solution, right? Because the purple graph is underneath the blue graph at that x value. So here in this particular example, the solution to the inequality f of x is less than g of x. It's an interval. It's the interval from A to B, right? Everywhere between A and B, the purple is underneath the blue. And because this is a strict inequality, it's an open interval. I should say the interval, right? And if I turn the inequality over, you can probably guess, if I had the inequality f of x is greater than g of x, this is asking, where is the graph of f above the graph of g? And again, the word where here means for what x values, or what inputs. So where is the purple above the blue? Well, for example, if you take an x value over here, let's pluck this guy out at random. If I look at the x value right over here, the purple is above the blue. So whatever this x value is, it would be a part of that solution. And in fact, anything bigger than b here would be a part of that solution, because the way this is drawn suggests that the purple stays above the blue forever. And also over here. Right, if I take an x value over here, like this, definitely looks like the purple is above the blue over there also. So the solution set for this inequality f is greater than g. It's a little more complicated than this. It's a union of two different intervals. It's everything to the left of A and everything to the right of B. That's negative infinity up to A. Oh, and parentheses here. Union with B to infinity. So this is the basic idea. This is kind of a nice general picture, but not every graph in the world looks like that. So, each one you have to think of on their own. So what I'm going to do now, I'm going to give you a particular f and a particular g, and we will look at those graphs and try to solve the corresponding equations and inequalities, all three of these. All right, let's do it. Let's do it. Let's look at an example. Give us three things. We're going to solve 2x squared plus 3 equals 5x plus 6. That's an equation. We're going to solve 2x squared plus 3 is less than or equal to 5x plus 6. And 2x squared plus 3 is strictly greater than 5x plus 6. We're going to do all this graphically. So in theory, we could solve each of these. What are you doing, camera? We could solve each of these things algebraically, but it's some amount of work, and the idea here is to get comfortable with doing this graphically. Each equation or inequality involves the same two functions, right? One function here is 2x squared plus 3. The other function is 5x plus 6. So I'm just going to give those a name. I'll call one of them f. And I'll call the other one g. Which should be 5x plus 6. In high school or college algebra or elsewhere, you've probably learned how to graph both of these functions. We are going to study quadratic functions kind of in their own right. Like I'll teach you exactly how to graph things like this. I am assuming that you remember how to graph things like this from high school, college algebra, somewhere in the past. All right. So I'm going to mark this as -1. I'm going to mark this as +1. And I'm going to use a slightly larger scale on the y-axis. It's like 10, 20, 30, and so on, because these both go pretty quick. F of x, 2x squared plus 3, that's a parabola with a vertex at 0, 3, opening up and kind of stretched vertically by a factor of 2. It looks like this. And the linear function, g of x equals 5x plus 6. That's a line with slope 5 and y-intercept 0, 6. So he looks something like straight lines, nice and straight. He looks something like this. My scales aren't quite right, actually. Let me scratch the 1 and -1 here. I'm going to tell you that the x-coordinate of this intersection point here is -1/2. And the x-coordinate of this intersection point here is +3. So now with this picture, we want to solve the equations and inequalities above. Let's start with the equation. What are we looking for?
Where the graphs intersect.
Yeah. Yep. Looking for the x values where the graphs of f and g touch. So what are those solutions?
-1/2 and 3.
Yeah, that's it. Nothing crazy, right? Okay. Let's look at the solution to the first inequality. 2x squared plus 3 is greater than or equal to 5x plus 6. Kind of in words, what am I looking for here?
Where f of x is lower than g of x.
Careful with the labels. Oh, let me see. I think I switched the inequality around. Yeah, this should be a less than or equal to, right? Not greater than or equal to. I'm sorry. Yeah, so you're correct. We're looking for places where f, the parabola guy, is beneath g. What sort of animal is this? Is this going to be like 1 or 2 x values? Is this going to be all real numbers? Is this going to be an interval, something else, ordered pairs?
Would it be like an interval for the x values?
Yeah, exactly. I'm looking for the set of all x values where the blue is under the purple, which is going to be an interval. What is the interval?
Would it be -1/2 to 3?
Yeah. And then we want to be a little bit careful about whether this should be an open interval or a closed interval. Is this inequality true when x is exactly equal to -1/2?
Yeah.
It is, right? Those guys are actually equal to each other at -1/2. So because this is a less than or equal to, we want to include this endpoint. And for the same reason, we'll want to include the 3. So if this was a strictly less than, then this would be an open interval. Since it's a less than or equal to, it's a closed interval. We saw that that can happen when we looked at how to do this algebraically. Weak inequalities often yield closed intervals, and strict inequalities always yield open intervals. All right, let's look at the last guy. In words, what am I looking for here?
Where f of x is above g of x.
Yeah, I'm looking for all the x values where the blue is above the purple. So for example, right here, the blue is way up here and the purple is down here. So whatever this x value is, I would want to include that in my solution. In here, I would not want to include that in my solution because the purple is above the blue there. But then anything to the right over here, the blue is back above the purple. So what is this going to look like?
Would it be negative infinity to negative 1/2 union 3 to infinity?
Perfect. Okay, so I'm putting the parens on the infinities because I know they always get parens. What kind of delimiters does the 1/2 and the 3 get?
Parentheses.
Also parentheses, right? Because that's a strict inequality. It's a fun fact of analysis that the inverse image of a continuous function is under an inequality like it's going to be an open set. All right, and the way we would think about it is negative 1/2 is not a part of this solution because if you put negative 1/2 in here, you get the statement, you get 2 things that are the same, right? You know that this and this are equal to each other at negative 1/2. And being equal is not the same as having one strictly greater than. Any questions on what we did here? Okay. Now in practice, to get a graph like this, that's got the intersection points labeled correctly and everything, you would have to do quite a bit of extra work. So the purpose of this isn't necessarily to give you a new strategy for solving equations and inequalities. It's more about helping you interpret or understand graphs. All right. The next thing we need to talk about is intervals of increase and decrease. We have an intuitive idea of what it means for a function to be increasing or decreasing. Again, here I'm just going to kind of draw a generic little picture. So maybe here's my function. I'm just going to label this as A. If you imagine a little dude walking along the graph, going from left to right, if he's going downhill, then the function is decreasing at that x value. And if he's going uphill, then the function is increasing at that x value. And the dude always walks from left to right. He can never go right to left. So Always walk in this way. Here, I would say that this function is decreasing from negative infinity to a and increasing from a to infinity. So just like with the inequalities and stuff we were solving before, the question is where is the function increasing or decreasing? And where always means for what x values. So I would say this function f above is decreasing and the word we use here is on, decreasing on the interval negative infinity up to a, and increasing on the interval a to infinity. And you notice I use open intervals here. There's a reason for that. There's several ways to think about it, but the simplest way to think about it is right there at that point. Imagine you are that dude. Right at that point, as you go through the bottom of that valley, you're neither going uphill nor are you going downhill. Very, very briefly there, you're not doing either of those things. So it would be wrong for me to say that this function is decreasing at x equals a. It would also be wrong for me to say this function is increasing at x equals a. And from the calculus perspective, finding where a function is increasing or decreasing turns out corresponds to solutions to a strict inequality, not for this function, but for another related function called the derivative. If the derivative is strictly positive, then your function is increasing. And if that is strictly negative, then your function is decreasing. So intervals of increase and decrease, this is worth putting in as a note. Are always open intervals of x values. And I want to double emphasize this last part. I know that if I give anybody in this class a graph and ask them to point to the part of the graph where you're increasing or to point to the part of the graph where it's decreasing, everybody could do that. Right? It's such an intuitive thing. But writing it down correctly is another matter. You wouldn't want to use the y value to tell me where you're increasing or decreasing, because there might be multiple points on that graph with the same y value. So like right here, suppose this point on the graph, you want to tell me that you're increasing here. Maybe this y value is 3. If you tell me that this graph or this function is increasing when y is equal to 3, I don't know if you're talking about right here or over here, right? Y would also be equal to 3 over here. So it's unclear if you try to tell me y values. Right? If you say this function is increasing at y equals 3, if you're talking about this point, you're right. But if you're talking about this point, which also has y equal to 3, then you're wrong. This is actually why the definition of a function is what it is. Remember, functions are relations or rules for pairing where every input can go to only one output. So if you tell me the x value you're talking about, you want to, so maybe this x value here is 7, right? If you tell me this function is increasing when x is equal to 7, I know exactly where you're talking about. Because this is a function, there can't be any other point whose x coordinate is 7. There can only be this one. So if you tell me increasing when x is 7, I know exactly what you're talking about. There can only possibly be one point. But if you try to specify through y values, there could be multiple points. And so that would be ambiguous at best. So again, the thing to remember, intervals of increase and decrease are always open intervals, open because, you know, at points like this, you're not going up or down, open intervals of x values. Don't give me ordered pairs. And please don't give me y values. Y values, they don't mean anything for this. where is something happening on a graph always means what at what x value. So with that in mind, I want to show you how we would define increasing and decreasing in a slightly more grown-up math class. It's the actual definition of increasing and decreasing. We say f is increasing on an interval, I'm just going to call it I, so if you're increasing, that means as you go from left to right, you should be getting higher and higher. If, you can describe this with an inequality. F of x2 is bigger than f of x1 for any x1 less than x2 in the interval I. So here we go. We said this function is increasing from a to infinity. So let me take just an x1. I'll take it right here. And x2 should be bigger than x1. So x2 is somewhere over here. The y value here is f of x1. The y value here is f of x2. So if x1 is smaller than x2, and both of those x values come from some interval where my function is increasing, then f of x2, the y value at the bigger x value, should be larger than f of x1. Similarly, we say f is decreasing on the interval I if f of x2 is smaller than f of x1 for any x1 less than x2 in I. Same thing, just turned around. So it says, if you take two x, increasing means if you take two x values, one bigger than the other, then the y value at the bigger x value should be larger than the y value at the smaller x value, right? As you go left to right, you go uphill. And decreasing means exactly the opposite. It means if you take two x values, x1 and x2 with x2 larger, then the y value on the graph at the larger x value should be smaller than the y value on the graph at the smaller x value. And this again hints at why we always use open intervals, because you need to be able to compare two things to talk about increasing and decreasing. If you're going to say you've got a closed interval on which your function is increasing, that means you're going to tell me that you're increasing at that endpoint. But at that endpoint, you don't have anything to compare to. It's just the single number. So open intervals are intimately related to this concept of increase and decrease. Okay. This is fairly easy to do if your graph is nice and smooth. But if your graph is kind of weird, maybe it's got some broken pieces, and maybe it's got some pointy pieces, it's not all nice and smooth, things can get a little bit trickier. So let me look at a slightly more complicated example. So let's find where this function f is increasing or decreasing. I'll draw the graph here for us. Let's start with something like this. Something like this. This. All right, pretty strange looking guy. We'll call this -1. That's positive 1/2. That's 2. And that's 3. So notice that to answer this question, I don't need to know any of the y values on the graph. I just need to be able to compare y values. I need to know their relative sizes, but I don't need to actually know any of their sizes themselves. And this is the graph y equals f of x. This is my x-axis. Okay, who can help me out with just one interval on which this function is decreasing?
2 to 3.
Good. And the thinking about the guy walking along the graph is the easier way to do this for sure. So guy walking along the graph here, he's for sure going downhill. So the open interval from 2 to 3 is part of that. Yeah. Is there anywhere else?
-infinity to -1.
Very good. All right, everywhere over here, this arrow implies that he kind of keeps going like that forever and ever. So if my little guy is walking along the graph all the way up to this point, it's going to go on downhill, 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 downhill. Yep, he's going to turn around and go uphill, 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 and then who knows, and then downhill, downhill, downhill. Right. So these would be my intervals of decrease. Okay, what about increasing?
-1 to 1/2.
Very good. Open interval from -1 to 1/2 everywhere in here. We're definitely going uphill. Where else?
3 to infinity.
Very good, right over here. So increasing can kind of look like two things. It can kind of look like this shape here, or kind of look like this shape here. There's actually names for this. We call this concave up, and we call this concave down. And decreasing can similarly be concave up or concave down. Decreasing, concave down. I don't have any examples of right here, but it kind of look like this. All right. So we are increasing from.
Do we say anything for whenever it goes from 1/2 to 2 when it's constant?
Ah, good question, right? So that's why I put this in here. As I'm walking along this, imagine the little dude, I ask those questions. Is he going uphill? Oh, no, because it's just horizontal flat. Is he going downhill? Also no, just horizontal flat. So in this portion of the graph from -1/2 to positive, or sorry, from +1/2 to +2, we're neither increasing nor decreasing here. So if you want to, you can kind of fill this in. This is decreasing. This is increasing. This is neither. This is decreasing, and this is increasing. And there's something kind of special about the point. Can't speak today. About the points, or the places, the x values, where you change from decreasing to increasing, or you change from increasing to decreasing. Those are kind of special. All right, before I move on, any questions on this example? for now, remember, you will be given the graphs. In the future, you'll have to cook up the graph yourself. But for the time being, we just want to get you comfortable with the language and notation. Okay. One last big concept here, and that is what are called extrema. And for whatever reason, our textbook, this author focuses just on local extrema. Another word for this is relative extrema. Extrema is a single word for mins and maxes. And those are what they sound like. They are places where the graph is either small or large, relative to other places on the graph. I prefer the language that your author doesn't use, right? Relative mins and maxes. But they mean the same thing. Again, let me draw a sort of general picture, and then I'll give you the rigorous definition. The points that I've just kind of put a little tick on there are special. If you draw a little window around this point, you see that the marked point there is the tallest point in that window. And if you draw a little window around this point, you see that the marked point there is the lowest point anywhere in that window. This is what it means to be a local max, and this is what it means to be a local min. So local means like nearby, right? When you talk about locally brewed beer, coffee, whatever, you're talking about stuff that was made nearby where you live. Here, local means nearby this X value. So let me say this is A, B, C, D. The technical definition, I will show you in a second, again, has to do with open intervals. But the intuitive thing, if you think you have a local max at, say, A, what you should do is imagine a little interval centered at A, little open interval centered at A, and then the window that creates for your graph. If the point on the graph is taller than any other point in that window, then that's a local max. And similarly, if you think you might have a local min at B, what you should do is think about a little interval centered at B, and then draw the little window in the graph that corresponds to that little interval. If the point on the graph at x equals b is the lowest point anywhere in that window, then that point is a local min. So this would also be a local max. And this would also be a local min. The tops of hills and the bottom of valleys. And if your graph is nice and smooth, like this, then you'll notice that local maxes are places where you go from increasing to decreasing. That's only true if your graph is connected and smooth. But again, if the graph is connected and smooth, then a local min will be a place where you go from decreasing to increasing. I'll show you some examples where things are not connected or not smooth, and you'll say that's not always true. But many of the graphs we play with will be nice, smooth, connected graphs. so that increasing to decreasing for maxes and decreasing to increasing for mins can be a useful way to think of things. So the technical definition the function f has a local min at x equals a means that the y value there should be smaller than any y values nearby. So how do we say that? Well, the y value at x equals a is f of a. That should be smaller than any y values nearby. So I would say f of a is smaller than f of x for any x values close to a. And the word close here is a bit of a mathematical cheat. What do I mean by close? Well, I mean, you can find some interval centered there where that inequality is true on that interval. And similarly, the function f has a local max at x equals a means same thing, just turn the inequality over. F of a should be bigger than f of x for any x values close to a. Now, one little further caveat, your textbook author does something weird. He uses less than or equal to and greater than or equal to in these definitions. I'm just going to say it, that's wrong. It's wrong. It's wrong. It means every point along a constant function's graph is both a min and a max. It's wrong. But that's what your author says. So I'm obligated to at least tell you that it's that way in the book. But every mathematician in the universe would disagree with them. They would say, no, those inequalities have to be strict for that to be true, because you don't want to call every point along a horizontal line a max. That doesn't make sense. But that would be a consequence of the definition in our book. So hopefully they fix that in the next edition. All right, let me show you some simple examples and some not so simple examples. You can have some of this stuff. Sorry. Simple and not so simple examples, mins and maxes. All right. Okay, let's do this one. Let's two. Give you those coordinates there, 2, comma. Actually, 1, comma 1. All right, and just for fun, let's call this function g of x. So what I'd like to do is identify any local mins or local maxes. And I'm also going to show you some vocabulary. Okay. Who sees a local min?
would one be 0?
Yeah, you caught the hard one first. Yes, there's a local min right here. This point is a local min. If I put a little window around the graph right there, the point at 0, 0, the one I didn't label, is the lowest point on the graph anywhere there. So g of x has local mins at one of them is x equals 0. The other thing I wanted to do with this example is give you the vocabulary we use. If I ask you, where is the min? I'm asking for the x value. Remember, where always means what's the x value. If I ask you, what is the min value? Then I'm asking for the y value. So at x equals 0, the min value is 0 there, right? Because this is the point 0, 0. So here's one of them. Anybody see another one?
2 1/3.
Yeah, this point is a local min. So the location of the local min here is 2. And the min value there is 1/3. Okay. And probably everybody sees that there's only one local max here, right? And it's this point. And the max value there is also 1. Does anybody know the name of the kind of weird behavior here at 0? It is a local min. That's correct. There's a special name for points on the graph that look like that. Oh, and Yanni asked a question in chat. Would 0, 0 be an absolute min? Yes. In this class, we don't actually talk about absolute mins and absolute maxes, at least not in this portion of the text. But technically 0, 0 is an absolute or global min also. So if that's language you haven't heard before, don't worry about it. I'm not testing you on it. You'll learn about it later. But Yanni, yes, that's correct. So this point is called a cusp, like on the cusp of something. Places where the graph is very, very pointy like that are called cusps, and they turn out to be really special in a certain area of number theory. The thing that hooked me so hard in mathematics is the kind of duality between these two different types of math objects. On the one hand, there are these things that you can count. They're called Farrer's graphs. They represent integer partitions. And on the other hand, you can come up with functions that spit these things out, that tell you how many integer partitions or Farrer's graphs of a certain type there are. And those happen to be what are called cusp forms. So spots like this are dear to my heart because functions that actually do this have some really neat algebra properties. Not that that is relevant to our course or even interesting to you guys, but fun facts. All right, let's look at one that's a little bit tougher. Same thing, I want to find mins and maxes. We've already seen something like that. Let's do. What other sort of bizarre shit could I throw at you? Should have something like that on both ends. Okay, that's all right. This is good enough. Alrighty. So let me say this is -1, this is +1. This y value here, we'll call this +1. We'll call this not quite at the same height. We'll call this 2. Okay. Same deal. Let's find mins and maxes. So when you've got wonky shit like this going on, we will have a slightly harder time finding minima and maxima. Yeah, I'll stop after this. We'll do this for our last example. If you got to run, you got to run. Does anybody see a min or a max?
Would the max be 2?
So one of the max values is 2. Yes. There's more.
Wouldn't it be -1 and then the max value be 2?
So let's be very careful about this. F of x, give me the locations first, has local maxes at. So where do we see a local max? What is the location of a local max?
One.
I need to label some other stuff here. We actually do not have a local max at 1. I see why you might think that, but it's actually not the case. Let me label these as 3 and 6 also here.
Wouldn't the local max be at -1?
Also tempting, right? So here's the game. Let me help you. X equals 0 is right here. I don't think we have one there. Remember what I suggested. If you think you have found one, a min or a max, draw a little window around the graph there. So let's look at what's happening at -1. At -1, here's a little window. I think there's something special going on here. What is the actual point on the graph at -1? What is f of -1?
1.
Yeah, f of -1 is the y value of this point. So if this was filled in up here, if I were to move this point up and fill that in, that would be a local max. But is this point, the actual point on the graph at -1, the tallest point anywhere in this window? Well, no, look, all these points up here on this line segment here are taller. All these points over here on this line segment are taller. This is not a local max. In fact, it's going to be a local min. Let's look at the other interesting points in the same way. Something funny going on here, right? The actual point on the graph at x equals 1 is right here. Is this the tallest point anywhere in this window? Hell no, there's all this stuff over here, which is taller. So that's not a max. What about at 3? The actual point on the graph at x equals 3 is up here. Is this the tallest point anywhere in this blue window? Yes, it is. Right? The other points in this window are along this little piece right down here and this little piece right over here. There is no point on the graph down here. It's up there. So the first local max we find is at x equals 3. And the max value is 2. Okay, any other local maxes?
X equals 6.
Very good. So your homework will sometimes say, don't include endpoints, but that's again, just the authors being lazy. This is definitely a local max. If I draw a little window around that, that's the tallest point anywhere in the window. So we have another one at X equals 6. And again, the max value is 2. I wasn't very creative with the Y values here. What's that? All right. And that's all the local maxes. There are none others. The only places that look like they might have something interesting going on, we've already ruled them out. So these two points are local maxes. Here, we said it already. This is a local min. If I put a little window around the graph at X equals -1, this is the lowest point anywhere in that window. So F has local mins at X equals -1, and the min value is 1. Okay, what about here? Is this a local min?
Yes.
This one's subtle, right? If not for the stuff over here, if I cover this stuff up, then that looks like a local min, because that would be the lowest point anywhere in that window. But this point is not, let me say, local min. Yeah. Okay, yeah, this is a local min, right? Yeah, this is the lowest point anywhere in this little window. Even over here where it looks like it's getting close, you can shrink it in. Nobody said how big your window has to be. There just has to be some window containing that as the lowest point. So yeah, this would be a local min. And that's it, right? So the min value. The min value here is, again, 1. Okay. So finding mins and maxes can be a little bit subtle. It's not always as easy as it looks at first. Your question, so Chris asked, when we're finding mins and maxes, they have to be the dark dots, not the open circles. That's true. The open circles are not actually points on the graph, remember? So this, there are points on the graph over here, and there are points on the graph over here, but right here, there's not a point on the graph. F of 3 is 2, not 0. Alrighty, my son's telling me it's definitely time to end the class, so I'm gonna go ahead and chop the meeting here. You do have another homework up that's due next Tuesday at the start of class, and we're gonna start talking about rates of change then. If you need to see me for anything, come by an office hour, message Discord, send me something on Canvas, and that is it. I'll see you guys next week.